Solid-state chemistry, also sometimes referred to as materials chemistry, is the study of the synthesis, structure, and properties of solid-phase materials, particularly, but not necessarily exclusively of, non-molecular solids. It therefore has a strong overlap with solid-state physics, mineralogy, crystallography, ceramics, metallurgy, thermodynamics, materials science and electronics, with a focus on the synthesis of novel materials and their characterization. History. Because of its direct relevance to products of commerce, solid-state inorganic chemistry has been strongly driven by technology. Progress in the field has often been fueled by the demands of industry, well ahead of purely academic curiosity. Applications discovered in the 20th century include zeolite and platinum-based catalysts for petroleum processing in the 1950s, high-purity silicon as a core component of microelectronic devices in the 1960s, and high-temperature superconductivity in the 1980s. The invention of X-ray crystallography in the early 1900s by William Lawrence Bragg enabled further innovation. Our understanding of how reactions proceed at the atomic level in the solid state was advanced considerably by Carl Wagner's work on oxidation rate theory, counter-diffusion of ions, and defect chemistry. Because of this, he has sometimes been referred to as the father of solid-state chemistry. Synthetic methods. Given the diversity of solid-state compounds, an equally diverse array of methods are used for their preparation. For organic materials, such as charge transfer salts, the methods operate near room temperature and are often similar to the techniques of organic synthesis. Redox reactions are sometimes conducted by electrocrystallization, as illustrated by the preparation of the Betschart salts from tetraethylethylamine. Oven techniques. For thermally robust materials, high-temperature methods are often employed. For example, bulk solids are prepared using tube furnaces, which allow reactions to be conducted up to circa 1100 degrees Celsius. Special equipment, for example ovens consisting of a tantalum tube through which an electric current is passed, can be used for even higher temperatures up to 2000 degrees Celsius. Such high temperatures are at times required to induce diffusion of the reactants, but this depends strongly on the systems studied. Some solid-state reactions already proceed at temperatures as low as 100 degrees Celsius. Melt methods. One method often employed is to melt the reactants together and then later anneal the solidified melt. If volatile reactants are involved, the reactants are often put in an ampoule that is evacuated, often while keeping the reactant mixture cold, for example by keeping the bottom of the ampoule in liquid nitrogen and then sealed. The sealed ampoule is then put in an oven and given a certain heat treatment. Solution methods. It is possible to use solvents to prepare solids by precipitation or by evaporation. At times the solvent is used hydrothermally, that is under pressure at temperatures higher than the normal boiling point. A variation on this theme is the use of flux methods, where a salt of relatively low melting point is added to the mixture to act as a high-temperature solvent in which the desired reaction can take place. Gas reactions. Many solids NaMN react vigorously with reactive gas species like chlorine, iodine, oxygen, etc. Others form adducts with other gases, for example CO or ethylene. Such reactions are often carried out in a tube that is open-ended on both sides and through which the gas is passed. A variation of this is to let the reaction take place inside a measuring device such as a TGA. In that case, stoichiometric information can be obtained during the reaction, which helps identify the products. A special case of a gas reaction is a chemical transport reaction. These are often carried out in a sealed ampoule to which a small amount of a transport agent, for example iodine, is added. The ampoule is then placed in a zone oven. This is essentially two tube ovens attached to each other, which allows a temperature gradient to be imposed. Such a method can be used to obtain the product in the form of single crystals suitable for structure determination by X-ray diffraction. Chemical vapor deposition is a high-temperature method that is widely employed for the preparation of coatings and semiconductors from molecular precursors. Air and moisture-sensitive materials. Many solids are hygroscopic and/or oxygen-sensitive. Many halides, for example, are very thirsty and can only be studied in their anhydrous form if they are handled in a glove box filled with dry gas, usually nitrogen. Characterization, new phases, phase diagrams, structures. The synthetic methodology and the characterization of the product often go hand in hand in the sense that not one but a series of reaction mixtures are prepared and subjected to heat treatment. The stoichiometry is typically varied in a systematic way to find which stoichiometries will lead to new solid compounds or to solid solutions between known ones. A prime method to characterize the reaction products is powder diffraction, because many solid-state reactions will produce polycrystalline ingots or powders. Powder diffraction will facilitate the identification of known phases in the mixture. If a pattern is found that is not known in the diffraction data libraries, an attempt can be made to index the pattern, that is to identify the symmetry and the size of the unit cell. Once the unit cell of a new phase is known, the next step is to establish the stoichiometry of the phase. This can be done in a number of ways. Sometimes the composition of the original mixture will give a clue, if one finds only one product a single powder pattern, or if one was trying to make a phase of a certain composition by analogy to known materials, but this is rare. Often considerable effort in refining the synthetic methodology is required to obtain a pure sample of the new material. If it is possible to separate the product from the rest of the reaction mixture, elemental analysis can be used. Another ways involves SEM and the generation of characteristic X-rays in the electron beam. The easiest way to solve the structure is by using single crystal X-ray diffraction. The latter often requires revisiting and refining the preparative procedures, and that is linked to the question which phases are stable at what composition and what stoichiometry. In other words, what does the phase diagram looks like? An important tool in establishing this is thermal analysis techniques like DSC or DTA, and increasingly also, thanks to the advent of synchrotrons, temperature-dependent powder diffraction. Increased knowledge of the phase relations often leads to further refinement in synthetic procedures in an iterative way. New phases are thus characterized by their melting points and their stoichiometric domains. The latter is important for the many solids that are non-stoichiometric compounds. The cell parameters obtained from XRD are particularly helpful to characterize the homogeneity ranges of the latter. Further characterization, in many but certainly not all cases, new solid compounds are further characterized by a variety of techniques that straddle the fine line that separates solid-state chemistry from solid-state physics. Optical properties. For non-metallic materials it is often possible to obtain UV-vis spectra. In the case of semiconductors, that will give an idea of the band gap. Bibliography. For a historical perspective, cf. Pierre Tessier, La Euro unregistered trademark, a copyright Mergence de la chimie du solide en France. De la formation d'un Euro unregistered trademark, une common auteur copyright Azar dispersion. Electronic version available, http://BDAU Paris 10 fr. Chapter 2 of Solid-State Chemistry and its Applications. Antonia West. John Wiley & Sons 2003, ISBN 981-253-003-7, cf. Chapter 12 of Elements of X-ray Diffraction, B.D. Cullity, Addison Wesley, 2nd ed. 1977, ISBN 0-201-01174-3, cf. Chapter 2 of New Directions in Solid-State Chemistry. Sienna Rao and J. Gopalakrishnan. Cambridge U. Press 1997, ISBN 0-521-49559-8, external links, 1, Satterway, Donald 3.091 SC. Introduction to Solid-State Chemistry, Fall 2010.